differences means electron survival probabilities, and the same formula just showed up here. Okay, and of course the important parameter is this amplitude, so-called mixed angle, and also this mass differences, mass square differences. So when you generalize to three generations, then of course the same matrix will have to use the 3 by 3, and usually it's a complex. And this is what we call the MNSP matrix. This matrix actually has a very similar, form as so-called the quark mixings. The strong interaction and also weak interaction for the quarks, they also mix. Okay, and but they have a very different, the so-called the forms. So in the neutrino sector, basically when you decompose, there are 3 mixed angles, and one so-called the CP phase, since this has to be complex, and also it's possible, okay, have another additional phases called the neutrinoless double beta decay. If the neutrino actually is not direct neutrino, you have some so-called we call the marijuana neutrino. Neutrino and the anti-neutrino may be the same kind. Okay, so this still has to be tested. But anyway, the for many years, I think before about 2006, then what we know, okay, is the theta 2,3, and the mixed angle is quite large, about 45 degrees. The theta 1,2 is about 32 degrees, and the two mixing, the so-called the mass square differences, it's delta m square 3,2. The 3,2 is 2.4 times 10 to the 3 electron volt square, and the delta m square 2,1 is about 8 times 10 to the 5. Okay, so if you actually try to draw, it maybe look like this. Okay, and one of the angle theta 1,3 was not measured at that time. So that time, okay, that's one of the reasons we proposed the experiment to try to measure this angle. We don't know how large, and there's no good model actually at that time to really predict these angles. And by measuring this, basically we should be able to figure out what the fraction of the so-called of each type, if each mass eigenstate in the flavor eigenstate. And this mixing matrix basically also gives us possible so-called CP violation. Okay, so the neutrino CP violation can, basically proportional to those products, the sine and cosine of those angles in phase. So, on the problem, of course, is the mass square differences. So we don't know exactly mass, we don't know mass square difference. So there's 2 solutions. So one we call the normal hierarchy, the other one called inverted hierarchy. We don't know which ones right now. And the normal hierarchy will be like this, and inverted will be like this. Okay. So this is still a problem, remain to be addressed. So how do we detect? And there are several different methods. And typically, if we use accelerator, I mentioned accelerator type experiment before, you can have a proton hitting the target and making the secondary, beams, and typically like a pions, kaons, and the pion will decay. For example, this pi plus decay to mu plus, and then the mu neutrinos coming out. Of course, the muon also can decay, and will be electron neutrino come out. So there will be some kind of mixed beam. Of course, using accelerators you can control, so you may have some kinds we call the horn magnet to select the sign of the secondary beam. And acceleration, oscillation, the probability actually is proportional to this kind of term. So called sine squared 2 theta 1,3 times sine squared 2 theta 2,3 times this oscillation term. Then the generally, if you produce the muon type neutrino, then you can try to measure, okay, so-called the electron type neutrino will appear. Okay, so this is we call it appearing experiments, and try to use to extract. However, there's many terms. It's not just one term, and the baseline usually is quite long. It could be 100 kilometer to 1,000 kilometer. As I said, okay, the matter effect also is there, and you have to really have to put into consideration. And of course, this is more expensive. The other type we call the reactor type, experiment. The reactor type experiment usually is quite close. The baseline is about a kilometer away, and that means if we try to measure θ13, it's the third one, and has to be quite close. And there's no matter effect, and there's only two terms here. Okay, and these two terms, this is basically compared with the first one. Is the first one dominant, and basically you can just see using this one. So this is before actually 2006 when we tried the post experiment. There are many limitations before from those reactor experiment. And part of the reason is the people try to build the experiment which doesn't want to put a lot of funding in there, so-called the quick and dirty type. And there are several experiments actually summarized here. You can see this is the distance in meter. So this is the 10 meter, 100 meter, kilometer to 100 kilometer. And typical precision of those due to limited statistics, because detector usually quite limited size, and it's about 3 to 6%. Energy spectrum usually we know from the reactor side. This also has to go through so-called the simulation of the reactor, and the time of variation of the fuel is also about 1 to 2%. The detector-related systematic usually is only one detector, and there's no good way to calibrate very well, so usually still remain to be around a few percent. So this is the experiment before. And that time we proposed the diabase experiment and try to measure the sine square to θ13 to about 0.01. You can see this is very small, oscillation. If we actually can measure well, and this is 1, this is 0.995, 0.99. Okay, and of course this one of the very important subject that time. And I think also the APS actually make a strong recommendation to do such kind of experiment. So the reactor-based the θ13 experiment, after in some initial competition in site, and remain to be 3. And one is the diabase in China, in southern China, in Guangdong. The other one is in Korea, the Reno experiment in Gongwon, Korea, and also in France. Okay, we call the double shells experiment. Okay, so these are the 3, at least right now, the competing experiments. You can see as I said, the reactor anti-neutrino, and each reactor actually usually have typically about several gigawatt thermal power. If we take a 3 gigawatt thermal power, can generate 6 times 10 to the 20 anti-neutrinos per second. So neutrino actually you can really have a lot of neutrino, except they don't like to interact. So very hard to detect. And as a matter of fact, if you sit here, okay, every second there are neutrino going through your body. You won't feel it. But from the reactors, the fuel composition and also the reactor running, and you can actually see this is the reactor running in days, and this is the different the field composition, you can see the spectrum. Okay, one's coming down in energy, and the other one is they change in time. Okay, so to do a more precise experiment, basically we have to know those spectrums to about the percent or better. To determine the theta 1,3 with the rect neutrino, as I said, okay, we have this kind of formula. It's a disappearance experiment for this electron type NTU-neutrino, and then we have to set a distance. We knew the larger one, called the theta 1,2, is already measured at time, and the theta 1,3 and should be, we know the limit is less than, I think, 0.15 that time. So we try to use 0.1, okay, in the proposal, and you can see it will give you a very small oscillation initially, and the distance for the far detector, that's the place we can measure the oscillation, somewhere around 1 to 2 kilometers, and the near detector actually we try to measure the flux, the initial flux, and we use so-called the far and near ratio. We measure so-called relative rate. Then actually there are many things cancel. Okay, there are good things. Then all the correlated error cancels in this formula, and then we can actually get a better control in systematics. So the knowledge at that time actually, this is already fast forward a couple of years before our discovery in 2012, and you can see there's some hint from different experiments. Some of the accelerated type like T2K and the MINOS. This is Japan, this is US, this is France, and double shows. All shows, marginally, the signals there, but we don't know if it's real or not. So how do we detect the ending electron ending neutrino? As I said, the inverse beta decay, we use this kind of reaction. We get a prompt signal from the positron and the delay signal from this neutron. The neutron actually, if we dope our detector with the so-called gadolinium, then we can increase the absorption of the neutron, the cross section, by a huge amount compared with just the product. So actually, we should be able to see both, because in both delay signals, one for the proton will generate so-called hydrogen. Okay, will generate the deuteron and the 2.2 MeV gamma rays, and from gadolinium actually it's 8 MeV delay signal. So it's different, energies. And basically, when we measure those events, we reconstruct those events, we can get the pretty good handle about the energy of the antineutrinos based on this approximation. So that big collaboration actually was formed in 2006, okay? And it has many institutions from the US, from Asia, and also a few from the Europe. In Taiwan, it's NTU, the National Jiaotong University, also the National United University. This is the collaboration meeting photos in Hong Kong in 2012. You can see in CU, Chinese University of Hong Kong. Okay. The Dabe nuclear power plant, and located about 55 kilometers from Hong Kong. Okay, so it has a 6 reactor in commercial operation. And it's about top 5 in the world, because we should have enough flux, which generate about 17.7 gigawatt thermal power. Okay, and you can see the Dabe, Dabe cores, the 2 cores over here, and then the so-called Ling-Ao 1, Ling-Ao 2, and it's sitting over there. So, as I said, we place the detector we call one near, one far. So based on this simulation, actually we can based on that simulation, we actually can design the experiment where we locate the experimental holes for the detectors. So we have two near detectors, and you can see the database over here is bisector of these two core. The Linao actually is over here, and it's rested in the middle line of these four. And the far detectors is over here. So in terms of distance, the far detectors is somewhere around 1.6 kilometer to about 1.9 kilometers away, and depend on those distance. And the near detector somewhere it's around the 400 meters, 400 to 500 meters. And the detector design, we took actually very special design with a concentric detector, and there are three detector volumes. The middle one we call the target volume, and doesn't work. It's 2010, okay. Up there, the 2010, the gadolinium, doped liquid cylinder. Outside the target volume, we have the so-called gamma catcher, the 20-pound liquid cylinder, and then outside the gamma catcher is the 37-pound the mineral oil as a shield. Then we have the 192, photomultiplied tubes to try to detect. So each unit actually is about 5 meters in height, 5 meters in diameter, so really huge. And the center one, we call the target volume, that's a 3 meter acrylic vessel. So all the one in the middle has to be light transparent. Okay. Then everything will be sitting inside the water shield. There's about 2.5 meter water shield to attenuate all the outside background. And here, I just show you with a cartoon of this kind of event when the NTU-Neutrino absorbed, break into the positron and generated 2 photons. This is about the 1 eV height, the 2 photon energy add up, about 1 eV plus the kinetic energy. Then with also the neutrons, which scatters and making the gamma rays. But the absorptions, so-called the delay signals, has a different time scale. For the gadolinium, has higher cross section, about 0.1% gadolinium is about 30 microseconds. For the proton hydrogen, it's about 180 microseconds. Okay. And the detector actually, you can see, with our simulation at time, and we can build, say, we want to build 8 identical detector modules, and the resolution basically is about 12% over E, and with the position, reconstruct the so-called vertex position about 1270. This is inside each detector. You can see there are 3 concentric volumes. And this is the most inner ones, the 3 meter one, the 4 meter acrylic vessel, and the 5 meter the stainless steel. And these are the phototubes. Okay. So this is one of the 3 meter vessels was produced in Taiwan, and it's a very thin wall. It's a 10 millimeter thick, 1 centimeter thick wall, and you can see the top and bottom is only about 1.5 centimeter. It's completely steel, only with some penetration on the top. So these 3 different volume of liquid has to be separate. Also, it's UV transparent down to about 300 nanometer thick. And experimental we need some kind of calibration to know the energy scale. So we built actually not only the energy scale, also to calibrate so-called the nonlinearity of the energy and position inside the detectors. So we have 3 units at the different locations. At the R equals 0, R equals 1.35, and also R equals 1.77. So this is actually sitting in just the liquid simulator. And there's 3 different sources on each d-axis. And there's a germanium 68, it's a 10 hertz, and it's a gamma source, and americium carbon source. This is a mixed source, about half hertz, and also the cobalt 60 gamma source, about 100 hertz. And also have the light LED diffuser diffuser ball, actually to really just monitor so-called the PMT gain and timing. So this is the photo of the assembly. You can see for each detector. This stainless steel vessel sit in actually a pit. It's a 5 meter. You can't see it down. Then we installed the so-called the lower reflectors, and it's quite large, 4.6 meter in diameter. Then also the acrylic vessels. You can see also install the PMDs coming down on the kind of panels, and install the top reflectors and close the top, and then install the calibration unit. So this is each, this installation takes many months. Also, we need to produce enough so-called liquid simulator. Okay, we talk about like 200 tons. Okay, so the 185 tons gadolinium loaded the liquid simulator, and also 196 tons liquid simulator. So, so these actually also produce the underground. We also monitor the long-term so-called the stability of those liquid. So it looks quite nice. And we also fill it. And to do the experiment, we actually have to monitor so-called how much target mass, how much actually liquid we fill in there, and based on weight, and also the so-called mass flow meters. So we have several ways to check it, and they all agree to quite well. Okay, you can see the relative acidity is about 0.02%. Then we lower the detector in the experimental hole, and you can see this is the near detector, and we have 2 of them. Once you fill with the water, and then on the top, we have to cover with the so-called RPC detectors to as a muon detection. And this is the other EH2 holes, this EH3 hole, the far hole. So by 2011, in December, we only have 6 detectors ready at that time. And but we do have a competition with the Reno. So Reno already started, they have 2 detectors, one far, one near. They started in August. And with 6 detectors, we think we can catch up in less than 2 months. From there, they need like at least 6 months, data taking. So we decided actually just go ahead with the 6 detectors. And this is actually we have very low threshold to trigger. It's like 0.25 photoelectrons for each PMT, and also we can do a multiple PMT as a sum as a trigger. The energy calibration also you can see is using cobalt 60. This is a cobalt 60 lines, actually quite well, and we can measure quite a bit. For example, using different source, we measure so-called the energy resolution. So we have to select so-called the anti-neutrino inverse beta decays. These are the selection, the criteria. The prompt is between 0.7 to 12 MeV. The delayed is peaked at 8, so we select between 6 and 12 MeV. The capture time is roughly about 30 microseconds, so we select between 1 to 200 microsecond. And there are other backgrounds like muons, we have to reject them. And these are the cuts. So basically, after those selection, you can clearly see, okay, the prominent delay, the scatter plot. This is delay energy. This is A and B. This is 2. This is the hydrogen. This is the gadolinium, and also you can see the prompt energies. So then we actually project out. You can clearly see, okay, data compared with Monte Carlo. They're more or less, give us the shape. And this is the delay, the A and B here. So we only select gadolinium for this analysis. There's another analysis actually doing the hydrogen, but hydrogen actually is more complicated because it's not just the central target. Outside the liquid cylinder also has hydrogen, so we have to do different analysis. But anyway, the neutron capture time you can see is about 30 microseconds to 29. These all 6 detectors all give you the same shape. So we can measure those capture time quite well. And the data set, okay, I'll summarize here. The first result, we actually published a NIM paper to compare the 2 detector comparisons side by side in the H1, because this was installed in August of 2011. So we took about 3 month data, and you can compare these side by side, and really, we controlled, so-called narrow down this systematics. So we know our systematics quite well. And the first oscillation analysis is taking 55 days data with 680 near and far, and published in 2012 in April. Then there's improved oscillation analysis about 140 days. Okay, the latest one we just published in February, February 14. It's 217 days, and so this is actually has also pretty good improvement compared with this one. So this is the data taking. You can see so far we actually analyzed it up to here, and these are we have more data taking since then with 8 detectors. So these are still right now in the analysis chain. So the initial result with this 6 detectors with 55 days, it was amazing actually that time. I remember in this meeting in Hong Kong, okay, and we're supposed to do a blind analysis. It means we don't want to look at the results. So it means some of the parameter actually was blinded, hiding, but we already see some hint. There's some oscillation seems there, and but of course so that was very exciting that time. So we want to publish it actually very quickly that time. So this is the first result actually in March. You can see we released in March. The EH1, EH2, they're very close, and they're very close to 1. But they are not 1 because the measured sine squared 2 theta 1 3 is quite large. It's 0.089 at that time with this kind of error. So then then the EH3 you can see V3 detector are also consistent. They're coming down. Okay, so the 6.
These 3 points are very close to EH3.
EH3 should be on top of each other, but we actually intentionally separate them out. They're supposed to be on top of each other. Okay. Now with all these data, okay, this is the current update. Well, we can collect probably more than 300,000 anti-neutrino interaction already. Okay, you can see the 81, the new detectors is about the 100,000 level, and the